Okay, so for this problem, we want to solve it using separation of variables. And by far the most important part of this problem is to understand the role between the dependent and independent variable. Because we see a y prime, we know that y is dependent, and therefore the x must be the independent. So first step is to always rewrite this as a dy dx in place of y prime equals x times y plus 2. All right, and now we need to separate variables, which means we want to bring all the y's to one side and all the x's to the other side, performing algebraic steps. So first step was going to be to multiply both sides by dx. And again, we're treating the dy dx ratio as a differential, and that will cancel out the dx's, and then we're going to divide both sides by the y plus 2. So divide both sides by y plus 2 as well. All right, and in the process of doing so, we end up with our variables separated. We end up with having the dy over top of the y plus 2, and that is equal to x times dx. And now we need to integrate both sides of this. And when we integrate both sides, the left side can be done with a substitution, letting the u equal y plus 2. The derivative is just 1, so there's no fractions or factors to worry about. So that's going to just end up being the integral of 1 over u du. And over here, integral of x dx, of course, is 1/2 x squared. So it's going to be a 1/2 x squared plus c. If we now integrate the left side, that's going to be the natural log of the absolute value of u is 1/2 x squared plus c. You may be asking yourself, well, why don't we have a constant on both sides of this? And the idea is that you could always bring the one constant to the other side and consolidate it and still have one constant. And now if we go in and we substitute, the u is the same thing as y plus 2. So this is the natural log of the absolute value of y plus 2 is equal to 1/2 x squared plus c. And whenever possible, we want to go in and solve for y. And in this case, we can do it with a little bit of algebra. We can first take the inverse of the natural log function, which is the exponential function, and apply it to both sides. So we end up with just the absolute value of y plus 2. And that's equal to e to the 1/2 x squared plus c. So we have natural log of y plus 2, absolute value of y plus 2 is equal to the e to the 1/2 x squared plus c. And now we can use the rules of exponents backwards. We write this as e to the 1/2 x squared times e to the c. Because remember, when you multiply two things with the same base, you add their exponents. Now, since c is an arbitrary constant, you can rewrite that as a new arbitrary constant, and it's customary just to call it c again. So when we write that over again, we end up with the absolute value of y plus 2 is now equal to a new c times e to the 1/2 x squared. And then you'll notice, if you think about the definition of the absolute value, that's the same thing as either the positive or the minus, depending on the value of y plus 2. And so because of that arbitrary nature of plus or minus, we can once again absorb that into that arbitrary constant c. So that actually turns into just a plain y plus 2 is equal to c e to the 1/2 x squared. And then as the next step, of course, we can go in and subtract 2 and remind ourselves that this y is a function of x. So y of x is e to the 1/2 x squared minus 2. And that is our general solution of this differential equation. We can now go in and solve the initial value problem and then state the interval of existence, and we'll do that in the next video.